It's a pencil day. Isaac's here, yeah.
Isaac.
He can't see you.
Yeah.
There, now he can see you. Wave to Isaac.
Isaac.
Wow.
Yeah, well now there's no more snowboarding now. Sorry, Isaac. Go snowboarding in the slush and grass. Okay. On Monday, I jumped into topic 711, but I had never shown you the very last problem on 710. You may or may not have caught that or noticed that. I'd like to show you that. I think a lot of you finished it in class, and I think a lot of people were understanding what was going on. So you might, if you go to 710 right now, you might actually have this done, and that's okay. Let me run through it, okay? The reason why I want to make sure I do that is because this is the last problem on topic 2 for your homework that is due this evening. Not the same, but darn, I mean, if you took this problem and had it next to your homework assignment, you would have a heck of a time not getting it correct. I would think so. Not a challenge. Not a challenge. But it's pretty much the same. So, okay, let me recap what this is, because it's obviously been, like 6 days since I last talked about this. I have a reversible reaction, and this reversible reaction is at equilibrium. It's at equilibrium at a temperature of 298 Kelvin. And they're telling me that these are the molarities of those equilibrium, these are the molarities of my chemicals at equilibrium. What we had done is we had set up K, and we had solved for K at that temperature. In part B, it said, hey, we're going to change the temp. We're going to crank up the temp, make it hot. Okay? Which way is it going to shift? Well, we have an energy term on the product side. This is exothermic. And if I increase temp, I'm going to increase energy. And as a result, I would expect that this equilibrium should shift to the left. Okay, that's Le Chatelier's principle, right? If I add something to one side, it's going to shift away from it. If I remove something from one side, it's going to shift towards it. So in this instance, an increase in temp is like adding energy. We add the energy and we need to shift left to reestablish equilibrium. In part C, it says, okay, we have now increased the temp to 398. What are the values of the molarities going to be at the new equilibrium, once it reestablishes equilibrium at this different temperature? What we need to do is set up an ice table and use these values as the initial and solve for new values at the different equilibrium. I have my reaction. I want to rewrite that. So I have H2O plus Cl2O giving me 2 HOCl. We'll make an ice table. Purple and red, that's obnoxious. My initial quantities are 0.115 for my reactants. And 3.22 for my product. In part B, we already decided which way we're going to shift, right? Temp's going up. We're changing the temp from 298 to 398. As a result, we should shift to the left. So when we're shifting to the left, I would expect the quantities on this side to increase, and I would expect the quantity on this side to decrease. They will go up and down based off of their coefficients, right? Coefficient of 1, 1, 2. So 1x, 1x, 2x. At equilibrium, we have this. I now can set up K and plug my numbers in. K will equal, oops, not KSP, wrong sheet. K will equal products over reactants. My product is HOCl and that must be squared because of the coefficient of 2. My reactants are H2O and Cl2O. And we know what K is. They gave us K. K equals 544. Now, just to take a quick little side tangent, at 298, the equilibrium constant was 784. At 398, the equilibrium constant is 544. Okay, well, what happens when you change the temp? Or when we increase it, we would shift left, right? If I'm shifting left, I'm making more reactants. It totally makes sense that the equilibrium constant should be smaller at 398. Because when I go from 298 to 398, I'm shifting from products to reactants. My K value should go down. And that's what we see. That's good. That matches what Le Chatelier's principle is kind of talking about. Okay, so I have this, and this equals my equilibrium constant at 398 Kelvin, 544. And I can plug in what I know. What I know is my product is 3.22 minus 2x squared divided by 0.115 plus x squared. I have this term times that term, which is just squared. I can take an early square root to make the math much more friendly. And when I do, I get 23.324 equaling 3.22 minus 2x divided by 0.115 plus x. I multiply both sides by the denominator, and I get 2.682 plus 23.324x equaling 3.22 minus 2x. I now want to combine my like terms, keep everything positive if I can, right? So I'll subtract the 2.68. I will add 2x, so I get 25.324x equaling 3.22 minus the 2.682, which is 0.538. Divide by the 25. And x should equal 0.0212. Okay, that's not the final answer. That's not what I want. What I want is the molarity of all of my things or all of my chemicals at equilibrium, right? So I have my two reactants and I have my product. The reactants are 0.115 plus x. So 0.115 plus 0.0212. I get 0.136. And for the product, I have 3.22 minus 2x. So 3.22 minus 2 times that quantity. And I get 3.18. I hope you had that done. I think a lot of you did. I think, maybe. Are there any questions? All right. Cool. Let's go to 7-Eleven. Let's finish that one up. There, now they can all see you, Isaac. Oh. Uh-oh, what happened to 7-Eleven? It died. All right. So yesterday we were talking about KSP. KSP is another equilibrium constant. It's an equilibrium constant for the solubility of ionic compounds or salts. Okay? In other words, how well does an ionic compound or salt dissolve in water? What you'll notice, or what you probably noticed from yesterday, is all of these values of KSP are crazy tiny. Okay? 10 to the negative 12, 10 to the negative 33rd, 10 to the negative 12, 10 to the negative 6th. Okay? What that's trying to say is that the value of K is really small. And as a result, the reversible reaction is favoring the reactant side. With every single one of these types of problems, the reactant is solid salt. If this side is favored, what that's trying to say is that it doesn't dissolve very well. When this dissolves, you get aqueous ions. If it dissolved really easily, the K value would be huge. And we would have the aqueous stuff be favored. But in all of these examples, the K value is tiny, which is trying to say that the solid substance is favored. The solid substance is the predominant type of chemical that exists. It doesn't dissolve well at all. Okay? So we had done a couple of these problems. Let's try one more. There was one more that I wanted to run through on that sheet, and then we got a couple odds and ends to tie off as well. A couple other concepts on this one too. But a lab was done on a slightly soluble solution of scandium fluoride to determine the concentration of fluoride ions. Use the KSP and calculate the molarity of scandium when it's all said and done. First things first, we need a reaction. Our reaction is going to be the dissociation of scandium fluoride. What's the charge of a scandium? Okay, 3+. So I have scandium, and what's the charge of a fluoride? So I have ScF3. Don't forget, the reactant is always solid in these types of problems. On the product side, then, once this breaks apart, I get Sc3+ aqueous, and I get 3F1- aqueous. Okay? Erica, save myself time. Erica has a conflict, and she's going to be showing up. No, it was not. Huh? All right. I'm going to keep teaching things. Okay, sounds good. So that's our reaction. Okay, we can set up K. K is products over reactants like it always is. It's just that in this instance, the reactant is solid, so we don't include it. So I have scandium 3+ multiplied by fluoride 1-, which gets cubed because the coefficient is 3. I don't know how much stuff is going to dissolve. They didn't tell me that. But I'm always going to just make that X. Okay? In KSP problems, we're just going to throw an X value in for whatever this initial amount that can dissolve is. Okay? Now, I don't know how much of this is going to dissolve, but how much is going to break apart? Nice, right? Yeah, all of it. It doesn't matter how much of an ionic or a salt compound dissolves in water. Whatever does dissolve will dissociate. So as a result, I don't know how much is going to dissolve, but what I do know is that all of it is going to break apart. And at equilibrium, I should have 0 of that molecule together. None of it. Because ionic compounds, when they dissolve, will always turn into aqueous dissociated ions. Okay, I didn't have any of this before it dissociates. Once it dissociates, I'm going to produce some. And the amount that I'm going to produce is based off of the coefficient in the balanced equation. At equilibrium, I will then have x and 3x. Let's plug in what we know. KSP is 5.81. I'm sorry, do I want to do it this way? I do want to do it this way. 5.81 times 10 to the negative 24. And that's going to equal scandium times fluoride cubed. Scandium is x. Fluoride is 3x cubed. Now, you have to be careful. This whole term is cubed. The whole thing. It is not 3x cubed. It is 3x cubed. There is a difference. What's that? Correct. 3x, the whole thing cubed. What's 3 cubed? Did somebody say 9? Now, your brains like squared numbers. So, careful. When I cube things, make sure you're actually taking the cube, not the square. 3 times 3 times 3 is 27. Yes. Okay, so I have 27x to the third power. Can I combine these? Is that mathematically allowed?
Yes. Yes. Sorry. But I was thinking condition. 27x to the fourth, yeah.
Correct. I can. I totally can. That's allowed. They're multiplied together, right? So I'm going to end up with 27x cubed times another x, which means I have 27x to the fourth. Right?
Yeah.
Cool. So I have 5.81 times 10 to the negative 24 equals 27x to the fourth power. We can divide by 27, obviously. And I have whatever the heck that is. Hold on. (2.15) times 10 to the negative 25th equals x to the fourth. Okay, how do I solve for x? I got a fourth root there. Now, let me start with a square root, right? If I have x, if this was x squared, we would square root. What's the exponent of a square root? 1/2. Right? It's yeah. So square root is 1/2. Third root is 1/3. Fourth root is 1/4. So in your calculator, you probably have a button that's like x root of something, but I don't even use that on my calculator. What I do is I'm going to take this, correct. I'm going to take this caret parentheses 1 divided by 4 equals x. That's what I do. You don't have to do it that way by any means. If you know where your x root button is and you know how to manage it and punch it in correctly, you can totally punch in a fourth root in your calculator. But if you don't find that button, if you don't want to deal with that button, just understand that a fourth root is to the 1/4 power. Just like a square root is to the 1/2 power. An eighth root is to the 1/8 power. Okay? So if I take that number to the 1/4 power, I'm getting x equaling 6.81 times 10 to the negative 7. Yeah? Cool. What do they want me to solve for again? They wanted, I guess I was conflicted with what I wanted you to find. I have, determine the concentration of the fluoride ions, and then I say calculate the scandium ions. So we'll just do both, I guess. Scandium is what we got. That's nice. Okay, it's that, and that should be molar. I didn't leave myself space, but that's a molarity, obviously, when we have brackets, right? For the fluoride, we would just need to take 3x. So 3 times whatever that was, 3 times 6.81 times 10 to the negative 7, and we get 2.04 times 10 to the negative 6. Okay. So let me recap how these work, right? We've kind of done it 2 different ways. I can either give you some molarity, okay? Sometimes that molarity is like the initial total quantity of that molecule, right? And then we can use that, set up the ice table, and eventually solve for KSP from those values like we did in the first couple problems. Or I can give you a molarity of one of my ions at equilibrium. Use that and solve for KSP at the end. Okay? Or I can give you KSP and ask you to solve for how much of these things dissolve in the solution. In that case, we have kind of this weird ice table with nothing but x's and zeros. But we can set that up algebraically and solve for the molarity of any of those pieces. And that's exactly what we did in this last one too. I gave you KSP. We set up an ice table with nothing but x's. We set up the expression for KSP, solve for x. Got a little funky. We needed to throw in a 4th root, but certainly solvable, not too bad. Okay? That's still here. I'm assuming that's maybe like starting to sink in. I hope so. If only you had the capability of manufacturing this sentence on your paper.
There's really no room.
Okay, a couple other things about KSP. KSP is the equilibrium constant of solubility. It's the equilibrium constant of like, hey, how much of this stuff is going to actually go into water? Now, in general, the value of KSP gives you kind of a snapshot of how much of that stuff dissolves. But we do have to be very careful in making comparisons. For example, here are the KSP values for 2 different salts, copper hydroxide and scandium fluoride. Now, copper hydroxide is obviously a base because it has hydroxide, right? But it's also a salt. It's also an ionic compound. Most bases that are solid, they don't dissolve very well at all. Okay? They really don't dissolve well. When we do base labs with strong bases in AP Chem or in any chem class, we generally use sodium hydroxide or potassium hydroxide. The reason being, those dissolve well. But if I tried to make a solution of calcium hydroxide, it's tough. That stuff does not dissolve well at all. A lot of hydroxide compounds just do not mix with water very well. But anyway, so I've got 2 of these salts, and I have their KSP values. If I just look at KSP, it's like, okay, well, this one's bigger, right? 1.6 times 10 to the negative 19 is a bigger value than 5.81 times 10 to the negative 24. You agree? So on the surface, it feels like, okay, bigger KSP, more of that should dissolve. But that's not correct in this instance. If you look at the far right, I have their solubilities. The solubility of the scandium fluoride is 6.81 times 10 to the negative 7. The solubility of the calcium hydroxide is 3.4 times 10 to the negative 7. So more scandium fluoride actually dissolves in solution than copper hydroxide, even though the KSP value is smaller than the KSP up there. So what the heck's going on? What's going on is we have to be careful with comparing KSP values. You can compare KSP if both of the ionic compounds you're looking at produce the same number of ions. Here's what I mean. When I dissolve this in water, I get 1 copper, 2 hydroxides. When I dissolve this in water, I get 1 scandium, 3 fluorides. Total of 3 ions produced, a total of 4 ions produced. They produce a different number of ions. So I cannot directly compare the value of KSP. If I try, there's a decent chance I'm going to screw it up. Here's another example of the same situation. Copper sulfide, silver sulfide, and bismuth sulfide. This produces 2 ions, 1 copper, 1 sulfide. This produces 3 ions, 2 silvers and a sulfide. This produces 5 ions, 2 bismuth, 3 sulfide. If I look at KSP, this is the biggest. So in theory, it feels like this one should dissolve the most. This is smaller, that's even smaller, 1.1 times 10 to the negative 73. Okay? Scientific notations for losers. Write that baby out. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And that'd be fun. And all, yeah, no thanks. And all the kids, when they first learn scientific notation, complain about it and say it's stupid. We should start with these. How stupid is it now? Right? It serves a purpose, especially when we start getting really obscure, right? Okay, biggest K, smallest K. So on the surface, it's like, okay, if I'm comparing these, that's the biggest, it should dissolve the most. But it doesn't. And the reason why I can't make that direct comparison is because they're not producing the same number of ions. If I have 2 examples of chemicals that produce the same number of ions, then I can compare KSP. Then it's safe, and I'm going to get it right. For example, if I compare Ag2S with CuOH2, this produces 3 ions. This produces 3 ions. The K value of this one is 1.6 times 10 to the negative 49. The K value of this one is 1.6 times 10 to the negative 19. This is bigger. Because they have the same number of ions, and this K value is larger, I can safely and correctly identify that this is more soluble than this, which it is. Okay? So if you look at KSP as a measure of solubility, which it is, we can only compare molecules that produce the same number of ions. If you start comparing different numbers of ions, you're probably going to screw it up because it's not possible. Or I should, at the very least, you've got to be extremely careful. Have a great day.
Thank you, you too.
It's almost done. It's a good thing. I think. Rocket League after school today, that's fun. Varsity team's 2-0, in case you were wondering. That's right. Noah Olson is the only senior. I've got a freshman, and I've got a sophomore, Garrett Goddard, who is Gavin Goddard's younger brother. Huh? Garrett's very good. He hasn't hardly played the game, and he's very high ranked for the number of hours he has. So.
Are you still a basketball?
I think so. I think that for the freshman kid might be better than me. He's pretty legit.
I thought you said they were like really good at that.
I said when I started the team, I'm like, if there's somebody on the team that's better than me, that's a good sign. His name's Kenneth Sayawang, I believe. He had an older sister here a couple years ago. She was in the home. But he's good.
Wow.
I was technically ranked higher than him in the one playlist, but you know, I don't know. I think it'd be pretty tough in a 1v1. Okay, enough about that. Temperature can affect solubility. What do you think? Do you think if I change the temp, would that mess with how much something dissolves? I think so. That feels pretty safe. Do you think the pH could affect solubility? If I tried to dissolve something in an acidic solution, or if I tried to dissolve that substance in a basic solution, do you think that would change how much dissolves? I think so. Changing the pH can cause a precipitate. What's a precipitate? It's when a solid, like, falls out of an aqueous solution, so to speak. It's like I have a nice colorless solution with stuff dissolved in there, and then I mix something else in there, or I mess with it somehow, and all of a sudden it starts forming a solid on the bottom of the solution. That's a precipitate. Okay? If I change the pH, do you think I could possibly mess with a reaction to produce a precipitate? Let me say this a different way. This is an equilibrium reaction, right? If something forces this to shift left, what do I get? I get precipitate. No. Stop highlighting things. Okay. If it shifts left, I'm going to get a solid precipitate. So, if I mess with pH, could a change in pH possibly push an equilibrium reaction to the left? Yes, it totally could. Changing the temperature can cause a precipitate. Potentially. Adding a common ion, for example. Let's say I added some scandium. What would that do? I'd shift it that way. And what's this way? Solid stuff, precipitation. The ion product, which is QSP, is like KSP, except that the equilibrium concentrations are not used for Q. Uh-huh.
Yeah,
I know.
I would erase it. But...
You should make it test with all the answers.
You made them all C.
Yeah.
That's just kind of, then it's like a psychology test within a test.
What if they did that in the
Yeah.
I
I
have.
had to order like 4 in a row.
Wait, what?
Oh, I didn't
know.
Okay. I was doing something like Proctor.
I was proctoring,
Yeah.
just stimulating. It was great.
Oh, Lucky, you would join me.
Who?
Julian?
After this, I want to use my proctor so bad.
We were done very early. We weren't messing around in my room. It was Clark and I, and it's like, okay, let's get this thing done. Breaks were like half the time.
Really?
Yeah, Julian.
I get a bad score. It's your fault. Oh. Oh. She's so
Sophie was in my room if you didn't gather.
I'm just saying, maybe if I got that extra 5 minutes. Oh my God.
Sounds like you're splitting hairs. All right, let's go over to 712. Nope. I know. Okay, so those true-false questions, or in other words, those true questions, were kind of leading us into this. 712 is on the common ion effect, also known as, hey, when something is soluble and you introduce a common ion, it's going to mess with the equilibrium. It's going to shift it and push it in a certain direction. That's what this sheet is about. The math will get a smidge funky, but hang with me. The pitchforks and the torches came out for a second last hour, but I was able to fight back the mob. So they were mad at me.
What did you do?
I was breaking math rules. You'll see in a second.
Oh, God. I'm very mathematically blind.
Oh, then you will not like this. Okay. But I can, there's the reason for why we do what we do, don't worry. Okay, so in a solubility equilibrium such as this, if I were to add either calcium ions or fluoride ions, which way would that shift the reaction? If I add either of these two things, I would shift left, right, to reduce that stress. If I shift left, am I increasing or reducing the solubility of that substance? What's on the left side? What's on the right side? Which side represents things being dissolved? That side. Which represents things not being dissolved? That side. So if I'm shifting left, I'm getting less stuff dissolved. I'm shifting towards the solid. So it is less soluble, right? So that would be a reduction in the solubility. Does that make sense, right? It's a matter of like, this is not dissolved, that is dissolved. I'm going that way. Okay, that sounds like I'm dissolving less stuff. To put it in very, very simple terms. Make sense? Find the molar solubility of calcium fluoride in a solution containing 0.01 molar calcium nitrate. Let me stop right there. What we're going to try to do today, compared to 7-Eleven. In 7-Eleven, I had ionic compound, and we're going to dissolve it in water. Today, I have an ionic compound, and I'm going to try to dissolve it in a solution that already contains other stuff. Okay, not pure water. I'm going to try to dissolve it in a solution that already contains some other things. So let's set up our ice table like we always would. This is what I'm interested in. I'm interested in the calcium fluoride. So I have CaF2, solid. I have calcium ions, aqueous as a product. I have 2 fluoride ions, aqueous as my other product. Whenever we do these solubility KSP ice tables, X is always this value right there. Now, I don't know what that is, but how much of it's going to break apart? All of it. 100% of whatever dissolves will dissociate. The initial concentration of fluoride will be what? Do I have any fluoride? Not yet. That's going to be 0. But this time, the initial concentration of calcium will be 0.01 molar because we are attempting to dissolve this stuff in a solution that already contains calcium. Calcium is a common ion, meaning it is shared between what I'm trying to dissolve and what I'm trying to dissolve it in, right? So I have a 0.01 molar of calcium, 0.01 molar solution of calcium nitrate. And I'm going to take some calcium fluoride and try to dissolve that solid calcium fluoride in that same solution. So what's happening is I already have calcium in my beaker. I already have that much calcium in solution before I even try to dissolve this stuff. Now, we got to read between the lines just a smidge. This molarity is for calcium nitrate. Calcium nitrate is an ionic salt compound. When this dissolves in water, what happens to it? It dissociates 100%. So this molarity of the whole thing, in reality, is the molarity of the calcium as well. It's a 1-to-1 ratio, right? If I wanted the molarity of nitrate, it would be 0.02. Right? Because the nitrate would be a 2-to-1 ratio for that whole molecule. The whole molecule is 1-to-1 ratio for calcium, so the molarity of calcium ions would be 0.01. If I wanted the nitrate, it would be 2-to-1, so I'd have to double that, it'd be 0.02. But in this instance, we don't care about the nitrate's just a spectator. Because we don't share the nitrate ion between our two chemicals. The common ion, the one that's shared between the two of them, is calcium. So that shows up in the ice table. All right, so where the heck are we going with this? So first things first. I guess I kind of gave it away. Which way are we shifting? To the right. Now, if you look at your initial values, how can you realize you have to go to the right? Well, you could solve for Q, right? Then compare Q versus K, because when we compare Q and K, it tells you which way you need to go. That would totally work. But we don't even have to do that much. You see that? That's 0. Can I possibly go from right to left if I don't have any of that one substance? Not possible. We have to go toward the products. If I don't have anything here, I can only go in the direction to produce some of it. Okay, so at equilibrium then, I have and that. We'll go back to purple. Let's set up K. KSP equals products over reactants. It's an equilibrium constant, just like any other one. I have my products, calcium 2+ and fluoride 1-. The reactants is a solid, so I don't include it. This whole thing's over 1. Okay, that doesn't do anything for us, right? We'll just ignore it. They gave me KSP. They tell me the KSP is 3.9 times 10 to the negative 11. So I have 3.9 times 10 to the negative 11 equaling my calcium, which is 0.010 plus x, multiplied by my fluoride squared, which is 2x squared. How's that algebra look? We've arrived. Now, if we try to do this like, you know, how algebra taught us, right? What we would have to do is we would square this term, so we'd have 4x squared. But then I would have to distribute that term to both of those. So I would have 0.04x squared plus 4x to the third power. I could remove an x squared term from both of those. And then, I don't know, doesn't sound like much fun, right? Maybe that does sound like fun. I don't know. Doesn't sound like fun to me. So what we're going to do is what I like to call math magic, which is not an actual term. That's just me saying dumb things. Okay? Here's what we're going to do. This is the original value of the calcium. When we shift to the right, we're going to add more. Now, if you look at K, K is ridiculously small, right? Crazy small. So when I shift from left to right, how far right am I actually going to shift? How many products am I actually going to make if my K value is that tiny? Very, very, very small amount. Crazy small amount. So here's what we're going to do. We're going to assume that this, even when we add it on, doesn't really affect that number. this is effectively insignificant when added to that. Because it's so stinking small. Now, why is x so tiny, right? Let me go back to where I came from. X is really tiny because it's the change. We're shifting to the right. But in order to reach equilibrium, we need way more reactant than we do product. Way more reactant than we do product. So how far right are we actually going to shift? Like a tiny, teeny amount. So small that this will not mathematically affect that. So what does that mean? We're going to ignore the plus x. Now, that feels like it should not be allowed. Good question. Now, so the other x. So the other x is coming from nothing, right? Now, is this really small? Yeah, it's really small. But the difference is this term is an original quantity plus that tiny change. So when I add that tiny change, literally, this is still just going to be that term, or that quantity. Over here, I can't make this 0 because then it makes the whole thing 0. So we are going to still solve for this value of x. It's just that this term, with or without that, is going to equal 0.01. That's the assumption we're making. It's the addition.
That's not necessarily.
No, not at all.
It's just a real count, so it would be-
So we're ignoring it, right? We're ignoring it in a mathematically allowed way. And here's the other thing too, is the way we do this is appropriately, we should totally check at the end that our assumption is within the threshold of what's okay. So this is called the 5% test, or the 5% rule. If this change is less than 5% of the original, we're good. It's okay to ignore it. But if we solve for x when we're all done, and the value of x is bigger than 5% of that, then we got to do something else. We got to do something called successive approximations. It's not bad. Huh? Yeah, that's why. No, it's really not bad. But here's what we'll do. We're going to ignore that thing. We're going to solve for x. I see you have a TI Inspire. Would you mind plugging that whole thing in with that value of x?
Like solve it?
Yeah, if you solve her and let us know what you get, including it. And let's solve it without it and see if, let's compare those numbers. I'm trying to prove to you that what we're doing is okay. All right, so let's solve this. We're going to ignore that. And now we have 3.9 times 10 to the negative 11 equals 0.01 multiplied by 4x squared, right? I'm just, squaring that term. I can combine these. So I have 3.9 times 10 to the negative 11 equals 0.01 times 4 is 0.04 x squared. Let me divide by 0.04. Obviously, I'm ignoring sig figs throughout the process. We'll deal with it at the end. There we go. 9.75 times 10 to the negative 10 equals x squared. We'll square root. And we get x equal to 3.12 times 10 to the negative 5. Cole, what'd you get using solver including the x?
Well, there's 3 different ones, but 2 of them are pretty much spot on. Because one is 3.11, or 3.12 e, or 10 to the negative 5th, and then 3.13 to the negative 5.
So, including the x, we get the same thing. Without the x, we get the same thing. What is that trying to tell us? It's trying to tell us that this doesn't change that. Whether we add that little change or whether we ignore that little change, this is pretty much going to equal 0.01. Now, let's do the 5% test. The 5% test is a mathematical check to hopefully show that we are allowed to do this. If the change is less than 5% of the original value, we pass and we're allowed to do what we just did. If the x is bigger than 5% of the original, we're breaking math laws and we've got to do it a different way. So I have my x value, oops, divided by the original amount multiplied by 100 to get a percentage. Okay, what percentage of my 0.01 is the 3.12 times 10 to the negative fifth? Oops. 0.312%. Is that less than 5? Yes, we're good. We're allowed to do what we did. Okay? So we are sidestepping the awful algebra. And we're sidestepping the awful algebra because we can. And it makes life way easier. It makes the math way easier. And it's totally allowed. And it's just, you know, as opposed to giving you all a TI Inspire, we can do it this way. Last hour they said, somebody shouted out, so you're going to give us all TI Inspires? And then I said, yes, look under your chair. Froston's favorite thing. No, there's not an Inspire under your chair. Or if there is, then it's somebody else's and you should give it to me so that they probably lost it. Yeah, those are like, what are they? Like $180, aren't they?
Yeah.
We'll pick that up there tomorrow. Thank you for your attention. Homework topic 2 is due tonight. It's all old stuff from last week.